Can you come up with definitions for acids and bases for Arrhenius, Bronsted-Lowry, and Lewis acid-base theory? How are Arrhenius acids different from Bronsted-Lowry acids?
Arrhenius acids are the entire compound.
Answer is they're not.
Bases.
Okay, they're the same. Hydrogen ion providers, right? We can call them hydrogen ion donors, hydrogen ion givers, hydrogen ion providers, same idea, right? An acid in both Arrhenius and Bronsted-Lowry acid-base theory is a substance that provides hydrogen ions, right? So, real quick, there's a lot of people that would call this is a 0.1 molar solution of hydrochloric acid. They would call this an acid. Is this, the contents of this bottle, an acid?
No.
It is not. It's a solution of an acid, isn't it? Right? Okay. Bronsted-Lowry and Arrhenius bases, are they different?
Yes.
Yes, they are. What's a Bronsted, what's an Arrhenius base? Compound that contains OH minus ions. Yeah? Sodium hydroxide, potassium hydroxide, lithium hydroxide, magnesium hydroxide, aluminum hydroxide. Those are chemical compounds that contain hydroxide ions. And when you dissolve them in water, they increase the hydrogen ion concentration, don't they? Okay? Now, I have a solution of sodium hydroxide. This is a 0.1 molar solution of sodium hydroxide. Is this a base?
No, it's a basic.
But it's a solution of a base, at least in the Arrhenius sense. It's a solution of sodium hydroxide, a base. We okay? Okay. Now, before we go on and talk about the others, I want to talk about the words acidic, basic, and neutral. Terms you've heard before, right? For instance, if I asked you what an acidic solution was, you'd probably have an appropriate answer. Well, you might have an appropriate answer. An acidic solution?
It's a solution with a pH of
pH less than 7, right? You've heard it before, right?
Yeah.
That's why I made that statement. Now, wait. That's not our definition for an acidic solution. Although it is true that an acidic solution has a pH less than 7, nothing wrong with writing that down, that's not the definition we're using. We have this balance of hydronium and hydroxide ions, don't we? If hydroniums go up, hydroxides go down. If hydroxides go up, hydroniums go down. If hydroniums go down, hydroxides go up. Yeah? Now, we define these three terms, acidic, basic, and neutral, in terms of this balance. When the two concentrations are equal, that's a neutral solution. And by the way, in water, what would their concentrations be in a neutral solution?
1 times 10 to the
1
negative
times 10
7.
negative 7 for each one, huh? And in fact, if you take the logarithm of 1 times 10 negative 7, what do you get? 7. And of course, neutral solutions have a pH of 7, right? We're just not going to define these three terms in terms of pH, but rather in terms of this balance of hydronium and hydroxide ions. Yes? And of course, an acidic solution is where hydronium concentration is higher than hydroxide, and a basic solution is where hydroxide is higher than hydronium. Have a lot of trouble with these terms when we talk to students about acids, bases, acidic, basic, and neutral solutions. For instance, I'll ask for the definition of an acid. People say anything with a pH less than 7. See the problem? Here's my 0.1 molar solution of hydrochloric acid. Is it acidic? What's the pH? 0.1 molar solution of hydrochloric acid. pH is 1. How did we come to that conclusion? Just a reminder, because HCl is one of our strong acids, every mole of HCl that I dissolve produces a mole of hydronium ions, right? So this solution actually contains very, very few HCl molecules. They've all dissociated. Did we introduce that term last time? They've all dissociated, given up their hydrogen ions to water molecules. Almost all of them, right? Since I added 1/10 of a mole of HCl to make this solution, it's a liter of solution, I have almost 1/10 of a mole. Within a fraction of a percent, 1/10 of a mole of hydronium ions in this solution. 1/10 of a mole per liter, take the log, change the sign, we get a pH of 1, right? We okay? Now, this solution is acidic. It has a hydrogen ion concentration of 10 to the negative 1, 1/10 molar. What's the hydroxide concentration? Hydronium is 10 to the negative 1, hydroxide would be 10 to the negative 13. Yes? You can do that without a calculator. If I said this, the molarity of this was 0.125, you'd need the calculator, right? Okay. So this is an acidic solution. How did it get that way? In other words, how does an acidic solution become acidic? How did this solution become acidic? Add an acid. Because in order for a solution to become acidic, in order for pure water to become acidic, we have to add something that's going to contribute hydrogen ions. So that's what an Arrhenius acid does. It's what a Bronsted-Lowry acid does. Right? So there's where the two terms are connected. The word acid and the term acidic. Acidic is an adjective we use to describe a solution. Right? An acid is a chemical compound that provides hydrogen ions. An acidic solution is a solution with higher hydroniums than hydroxides. They're connected because in order to make a solution acidic, you need to add something that's going to contribute hydrogen ions. Yeah? I'll caution you, from a Bronsted-Lowry sense, can we simply add an acid to water and make it acidic? Take a look at your acid-base table. Got it out? According to Bronsted-Lowry, acid-base theory is hydroxide ion an acid? Can you find it on the left-hand side? Hydroxide ion is an acid, but what happens if I add hydroxide ion to water? The pH goes up, doesn't it? Right? Hydroxide ion starts with an A, amphoteric. It can take on hydrogen ions and become water. It can lose hydrogen ions and become oxide ions, can it? The conjugate base of the hydroxide ion is the oxide ion. Are we okay? So we can't simply say to make it a solution acidic add an acid because hydroxide ion is an acid, isn't it? Okay? Okay, and this solution is basic, isn't it? This is a 0.1 molar solution of sodium hydroxide. What's the pH? 13. Hydroxide concentration, 0.1. If it's 0.1 molar sodium hydroxide, it's really 0.1 molar hydroxide ion. There are no sodium hydroxide molecules in this solution, are there? Even though we write it right on the label, 0.1 capital M NaOH, there's really no NaOH in here. It has separated into sodium ions and hydroxide ions, hasn't it? And one hydroxide ion for every mole of sodium hydroxide I added. To make a liter of this solution, I had to add a 0.1 moles, 1/10 of a mole of sodium hydroxide. Okay. Hydroxide concentration is 10 to the negative 1, so hydronium concentration must be 10 to the negative 13. Again, when we're nice even powers of 10, we can do that in our head. And of course, if the hydronium concentration is 10 to the negative 13, take the log, change the sign, you get 13, don't you? Right? Again, if this was a 0.125 molar solution of sodium hydroxide, you'd have to use your calculator to figure out the hydronium concentration and to take the logarithm, right? But you could do that, right? Think about where I was. Acidic, basic, and neutral. Base and basic. Basic is an adjective we use to describe a solution, describing this balance between hydrogen and hydroxide, right? On the other hand, if I want to make a solution basic, what do I add? A base. Now again, we have to be careful about that as well, right? Do we have bases that we could add to water that would make the water acidic? Bronsted-Lowry bases, not Arrhenius bases, but Bronsted-Lowry bases. For instance, the bisulfite or bisulfate ion, HSO4 minus. Is it listed with the bases in your chart? HSO4 minus? Huh? But it's also an acid, isn't it? And if I added HSO4 minus to a water, it would make the solution acidic. Sodium bisulfate is typically what we add to swimming pools and hot tubs to lower the pH. If you've ever adjusted the pH in a swimming pool or hot tub, we use sodium carbonate to raise the pH. Typically, we use sodium bisulfate to lower the pH. How are we doing? Okay, acidic, basic, and neutral. We all right? Okay, back to talking about it, definitions of acids and bases then. We've defined a Arrhenius base as something that is a provider of hydroxide ions. What's a Bronsted-Lowry base? Hydrogen ion acceptor, or hydrogen ion taker, or a hydrogen ion taker, acceptor, receiver, good, receiver. All those words would work. The typical definitions are donor and acceptor, but you know the other words work just fine. And what sort of things can be Bronsted-Lowry bases? Can hydroxide ions? Is sodium hydroxide a Bronsted-Lowry base? No. It's an Arrhenius base, but not a Bronsted-Lowry base. But it is the hydroxide ion that could act as a Bronsted-Lowry base, right? And other negative ions, yes? Obviously, to a greater or lesser extent. We have some negative ions that are really not very good bases at all. Name one. Chloride ion, perchlorate ion, bromide, iodide ion, nitrate ion, sulfate ion. Those are not very good bases, are they? On the other hand, we have some that are very good. Sulfide, carbonate, hydroxide, oxide ions. Yeah? Okay. Move on to Lewis acid-base theory. What's the big change there? Instead of talking about hydrogen ion donors and acceptors, or proton donors and acceptors, the Bronsted-Lowry talks about, we talk about electron pairs. And something that is a hydrogen ion acceptor is really a electron pair donor from a Lewis point of view, yes? And what's the difference because of that? What's the difference between a Bronsted-Lowry base and a Lewis base?
There's more Lewis bases.
Nothing. Right? All the Bronsted-Lowry bases are also Lewis bases. Everything that's a Lewis base is also a Bronsted-Lowry base. Because if you've got an electron pair to donate, guess what you can do? Take hydrogen ions. And if you can take hydrogen ions, guess what you've got? An electron pair to donate. Yeah? The bond that is made between a Bronsted-Lowry base and a hydrogen ion is made with an electron pair. It's a covalent bond.